Today's May 31st, 2011. You guys are on text page 433, blue notebook page 370. We're on lesson 7.7. This is the last lesson before your test on Thursday. I'm going to go right into it. So, we're working with a formula much like yesterday. So, we're going to go right into it, the formula for today, which was very, very similar to yesterday's formula. They use the same types of letters. So, P at N equal to PO, 1 subtract R to the power of N. So if you guys remember yesterday, we were doing growth. Growth rates, R standing for a growth rate. This formula is decay rate. So this is something that is disappearing. Decay rate. This is the formula we're going to do. It is pretty much the exact same formula as yesterday's. The only difference is that is a subtraction sign other than yesterday's, which was an addition sign. So everything stands for the exact same stuff. We'll write it down again. P at N is our final number. Number or amount. P at O is our initial number or amount. Yeah, always have one there. R is the rate of decay in this case. And N is number of periods once again. So as long as you are familiar with yesterday's stuff, this should be quite easy. We're going to go right into the first question. The very first question they've given us talks about a scuba diver. So we'll call it example 1. There you go. Example 1, there's a scuba diver. He has a camera that takes pictures underwater. The camera can only take pictures with a minimum of 60% reduced light. The scuba diver also knows that light reduces at 2% per meter below the water surface. So he's now at 23 meters below. He needs to figure out if his camera can take a picture at that level. So our initial amount of light. Anyone know what our initial amount of light would be? So our P at O. What percentage of light when he's at the top of the surface will he see? 100%. We're looking for our, you know what, let's write the formula out again just so we have something to compare to. So let's write this formula again. P at N is equal to PO, 1 subtract rate of decay, number of periods. So we're trying to solve for our P at N. We need to know how much light there is 23 meters below the surface of the water. We know the initial value of light is going to be 100%. The rate of decay, we found out, was 2%, which we need to turn into a decimal. That's an arrow. So that is 0.02 when we go to plug it in. And the number of periods. What is the number of periods? 23 meters. That rate of decay is for per meter. So we are 23 meters, which means we have gone through 23 periods of decay. So our N will be 23. We're going to simply plug those into our formula and try to solve for what our percentage of light is right now. So let's say P at N is equal to, our P at O is 100. 1 subtract 0.02 to the power of 23. 100, 0.98, that's 1 subtract 0.02, the power of 23. So next thing we're going to do is the exponent. 0.98 to the power of 23 equals 0.6283, blah, blah, blah. I'm just going to take the answer from above to keep it more accurate. I need to multiply that by 100%. Or sorry, 100. And this says there's 62.83. What does that mean? 62.83 what? Percent of light. Can his camera take a picture? Why? I'm glad one person knows. Excellent. Okay. Okay, we're going to take up a difficult question here. With the same information, I want to figure out roughly what meter his camera stops working underwater. So, we know that, what are the minimum requirements for his camera? 60. So our new, let's write the formula over again. P at N is equal to PO, 1 subtract RN. If his camera's minimum requirement is 60% light, that means our P at N is going to be 60. We know that the P at O is 100%. We start with 100% light at the surface. That stays the same. Our rate of decay is still the exact same. It's 2%. And as a decimal, 0.02. What we don't know are the meters. We're going to use a estimating method to figure this out. No, we solved for the rate of growth yesterday. We have yet to solve for any number of periods. Guarantee you we didn't. Okay, so let's plug those numbers in. We're going to have 60 is equal to 100 multiplied by 1 subtract 0.02. N is our variable. We've never had an exponent as our variable. So, like Lewis said, the very first step here, or actually what I'm going to do is I'm going to equate the bracket first. So, 1 subtract 0.02 is going to give me 0.98 to the power of n. Like Lewis said, I need to divide both sides by 100 because in this case I'm trying to isolate my n. So I divide by 100. Oops, forgot that does that. So we're going to get 60 divided by 100 is equal to 0.98 to the power of n. 60 divide 100. Anyone know? 0.6, that's right. 0.6 is equal to 0.98 to the power of n. Now, this is where we get into trouble here. I haven't shown you, nor are we going to be working with the exact equation to work with this. So what we're going to do is we're going to kind of trial and error to figure this out. I need to figure out what 0.98 to what exponent will end up equaling 0.6. Okay? Now we know that 0.98 to the power of 23 gives us what? Anyone remember? 62. That was our answer before. So obviously we're going to need a greater number than that because we know he needs to be less meters below the ocean. So we know that 23, we'll do it in blue, doesn't quite work. 0.98 to the 23rd gives us 62, 0.62. That's too high of a number. So our next one we're going to try is 0.98. Shall we go to 24? Okay, let's try 24. 0.98 to the power 24. 61. Still too high, probably. Want to jump to 26? Sure. That's not a bad strategy either. So we're going to skip to 25. We're going to go to 26. See what happens. 0.98 to the power of 26. Hey, we're just below. Oh, let's check the 25 just to make sure. 0.591. We want to see which one's going to be closest. We won't be exact. So let's try to the power of, that's annoying, 25. 0.3. So, from this information, are you kidding me? Wow. Okay, so from this information, and actually that wasn't exactly, that was 0.3. Whoops. At what point, I want you guys to try to make sense of this. At what point will his camera stop working? Is it at 25 meters? Because I'm pretty sure his camera still works at 25 meters. Well, we know at 26, so that's well below. How about you give me a range? That's what I'm looking for. Very good. I'm looking for an answer that says between 25 and 26 meters, his camera will stop working. We don't have an exact amount, and I highly doubt he's going to have a meter stick underwater measuring. But we know that anything past 25 meters, most likely his camera will stop working. That's what an answer I'd be looking for, some kind of range. I don't expect you to have an exponent 25.3, have it dead on. I just want a range, somewhere like that. Do you guys understand that? So, gentlemen, I just want to get this through your heads. Exponential. Whoops, that's way too high. We know our exponential graphs and our decay graphs. Where their y-axis is going to be. Anyone remember? Never mind, I'll just teach it. All right, gentlemen, just as a recap, this is a growth. This is exponential growth. This is an example of what the graph will look like. At y, it's most likely going to be crossing at 1. And a decay graph, or exponential decay, is going to look like this. Two very different graphs for growth and decay. Just going to give you right to your homework. Okay, your homework, blue notebook, page 372, text page 438. 1, 2, 5, 8, 11, 12. Oh. I'm going to make sure you guys can see all of this. Oh, that's not what I see. I'll scroll down slowly in case you need to take this note.